Hello everyone, welcome to this lecture 28 of the NPTEL course on Riemannian geometry. As I was saying in my previous lecture, we are almost at the halfway stage, and I thought that instead of moving on to the next part of the course, namely metric geometry, maybe for the next 2-3 lectures we should have some fun. And so I thought I'll talk about the sum angle property for general polygons on curved surfaces. So this is something that I already I think stated in the first couple of lectures in this course, but now we will try to rigorously prove that theorem, the so called local Gauss-Bonnet theorem. And of course, as with all good things in life, nothing comes for free, and so we will actually have to work quite hard, especially in this lecture and the next one, and then in the 30th lecture we will sort of just put the final finishing touches. Okay, so the setup is as follows. So for the next 3 lectures, let M2G be an oriented Riemannian manifold of dimension 2. Okay, and let dA be its area form. So recall this is a construction that I talked about I think back in maybe lecture 7 or 8, that given a Riemannian metric on an oriented Riemannian manifold, one can talk about the volume form. So that's a natural nowhere vanishing top form associated to any Riemannian metric, and of course in dimension 2, instead of using the word volume, we use the term area, right. So we have this area form. So so now the first thing I want to talk about, so most of today's lecture will be about stating the local Gauss-Bonnet theorem. For that we have to develop some notation, so that is what I will talk about for most of most of this lecture. So the first thing I want to talk about are polygons. So just to draw a picture, these are basically curves that look like this. Okay. So more formally, here is a definition. So a piecewise smooth curve on M is a continuous function. So I should insert the word parametric. So whenever I say curve, I actually do not just mean the set theoretic image that I see on M, but actually a curve which comes with a parametrization. Okay. So piecewise smooth curve on M is a continuous function gamma, let us say from a compact interval a to b to M, such that there exists a partition I will always denote my partition as a naught, which will be the initial time a, less than a1 etc, less than am, which will be the final time b. So just to draw a picture, this is a to b, my partition may look like something like this, right. So the individual parts need not of course have the same length and so on. Okay. Such that there exists a partition such that gamma restricted to the interval ak minus 1 to ak is smooth for all k. Okay. So so note that this means that there exists, so what does being smooth on a closed interval mean? That just means that there exists a smooth extension to a open interval containing this compact interval. Okay, so for some delta k positive. Okay. So then we define the one sided velocity vectors at these potentially non smooth points by just taking the limit. Okay. So gamma dot ak plus, so the idea is here you have ak, so you take the velocity vector as you approach ak from the left, that is called gamma dot of ak minus, if you approach from the right, that is called gamma dot of ak plus. And the fact that these limits exist and in fact are unique is because this is a smooth, gamma is a smooth function on this compact interval, right. So these limits exist. So next we say that gamma is simple if gamma restricted to the open interval a to b is 1 to 1. So the only potential intersection point is at the initial or the final point, and it is closed if gamma of a is equal to gamma of b. Okay, we also call it regular if for all t not equal to one of these non smooth points the velocity vector is non-zero. Okay. So a remark is that by convention we always assume that gamma dot of a is equal to gamma dot of b. Okay, so for instance, if your curve has this form, then the non smooth points are basically these, but by convention, by maybe reparametrizing, I always assume that if I am working on a closed curve, so by convention if gamma is closed, we always assume that the endpoints are basically smooth points, right. So the points gamma of ak, where k now ranges from 1 to m minus 1, are called the vertices of, or called corners, are called the corners of gamma. Okay. Right, so now I can define what I mean by a curved polygon. So a curved polygon, a curved oriented polygon in M is a simple closed piecewise smooth curve with unit speed. Okay, so that just means that at all these smooth points gamma has unit speed. Okay, so in this case we call the collection of these corner points where k goes from 1 to m minus 1, the vertices of the polygon. Okay. So then I also have a notion of an external angle or an exterior angle, because remember we want to state essentially a generalization of the sum angle property. So the exterior or external angle the external angle at one of these vertices is defined to be the unique angle denoted by epsilon k between minus pi to pi, such that cosine of epsilon k is of course given by this the formula that we would expect. We are dividing by these, but note that these things are just one, right, because we have parameterized so that our curve has unit speed, okay, and the sign of epsilon k is positive if gamma dot ak minus comma gamma dot ak plus is an oriented basis for the tangent space. Okay, negative otherwise. Okay, so let me draw a picture. So let us say you have a curve like this. So this is gamma of ak. So these are the sort of two tangent vectors from the left and the right, and let us say your curve is oriented so that you come into the intersection in this direction. Then in this case if it were on the plane, then the standard orientation of the plane is that any counterclockwise direction is positively oriented. So in this case here epsilon k would be positive. On the other hand, if you approach the same intersection but in the other direction, then of course in magnitude your angle would be the same, but here epsilon k would be negative, okay, because you are moving in the clockwise direction to go from this to this. Okay, so maybe a couple of remarks. We assume throughout that there are no cusps. I.e. gamma ak minus should not be equal to minus of gamma dot ak plus, right. So you should not have a picture that looks like this, because if that is the case, then there is no nice way of defining the external angle. So we do not, because the external angle, I mean there is no nice way to see if the external angle should be 0 or pi, okay. So we do not want or minus pi, so we do not want any cusps. And the second point is that this forms an oriented basis. So this is a general statement. UV forms is an oriented basis for let us say the tangent space at a point P if and only if the area form, which is a 2 form, evaluated on u v, the area form at P, this is positive, right. So, a way to check whether you have an oriented basis or not is to just evaluate the area form on it. Okay. So, so I need another couple of definitions before I can state the local Gauss-Bonnet. So, so let gamma be a regular curve, be regular and smooth, let us say. Okay, so we let n of t. So, the idea is that if you look at this curve, you already have the velocity vector, you want to define a vector that is orthogonal to the velocity vector. So, that is going to be this n of t. So, we define n of t to be the unique tangent vector to m at gamma of t such that n of t is a unit vector n of t is perpendicular to gamma dot of t and gamma dot and n form an oriented basis. So, if you apply the area element to these two, that is positive, okay, i.e. this is an oriented basis. Okay. All right. So, again in this picture for instance this would be n of t. So, in the picture that I have drawn this would be n of t, whereas here in this picture it would be, so you have to apply the sort of right hand rule. So, if you have to rotate in the counterclockwise, right. So, here the n of t would be this, okay, and the opposite would be the case in the other picture. All right. So, so let me maybe make a quick observation. So, let gamma be smooth curve which is parameterized to have unit speed, okay. So, the speed is constant 1, then this is a calculation that I have done before. One can check that the intrinsic acceleration, which is the covariant derivative of gamma dot along gamma, this is actually perpendicular to the velocity vector. Why? Because as I said, I mean this is a calculation we have done many times. You simply differentiate the speed squared, right, that is 0 because it is constant 1, but then by the metric property of connections this is simply this, okay. All right. So, then that leads us to the next and the final definition before I can state our main theorem, is that if gamma is smooth with unit speed, we define its normal curvature by, you look at the intrinsic acceleration. So, technically this would be something times the velocity vector plus something times the normal vector, right, because at any given point the normal vector and the velocity vectors, they span the tangent space, right, they are orthogonal and we are working with 2-dimensional vector spaces. But because of this calculation and the fact that the intrinsic acceleration is perpendicular to the velocity vector, it will not have any component along the velocity vector. So, we can always write the intrinsic acceleration as simply some scalar which I will denote by kn of t times n of t. So, this kn is what is called as the normal curvature. Okay. So, it could be both positive or negative depending on how your normal vector is oriented with respect to the velocity vector. So, for instance, if you go back to this picture, here you see that the tangent vector is actually turning towards the normal vector. So, here this kn would actually be positive, okay, and in the other picture the kn would be negative. Okay. Alright, so now I can state the local Gauss-Bonnet. So, maybe I will use a separate page. So, here is the local Gauss-Bonnet. Okay, so let omega be an open set in M such that, so a couple of conditions. Omega is completely the omega closure is completely contained inside U, and U is a coordinate neighborhood. Okay, so we are only looking at small regions that are contained inside, whose closure is completely contained inside a coordinate neighborhood, and we assume that the boundary of omega is a positively oriented. I will explain what positively oriented is in a minute. Positively oriented curved polygon. Okay. So, suppose the external angles as above. So, I am going to use the notation from above where we defined what a curved polygon was. So, suppose the external angles are epsilon k, where k goes from 1 to let us say m minus 1. So, it is a polygon with m minus 1 vertices. Then we have the following formula, that if you sum up the external angles, then in the plane that would amount to being 2 pi, but here there are some correction factors that come from integrating the normal curvature on the boundary plus integrating the total Gauss curvature inside omega. This entire sum has to be 2 pi or is equal to 2 pi. So, where k is the Gauss curvature of the So, recall that just means that k at any point p is simply the sectional curvature of the tangent plane at that point, right. So, let me make several remarks. Firstly, what does positively oriented mean? So, positively oriented with respect to Stokes' theorem. So, the orientation that you use in Stokes' theorem, I am going to use that same orientation for the boundary of omega. So, that just means that if this is the curve that is the piecewise smooth curve parametrizing the boundary, then if you take the the outward normal to the boundary. So the outward normal to the region at the boundary, that and the velocity vector is an oriented basis. Okay, so that is the orientation that you use when you prove Stokes's theorem. Okay, so that, eventually in the last step of the proof we are going to use Stokes's theorem, so we need this the correct orientation. The second point is that if gamma is a parameterization of the boundary as above, so that means you have this partition of A to B as before in the definition of what it means to be a piecewise smooth function, then my notation is that the integral on the boundary. So of course this makes sense only at smooth points, right? The normal curvature only makes sense at smooth points. So what I mean by this is simply this summation. Okay. So take this as a notation or a definition. Okay. All right. So I hope the local Gauss-Bonnet theorem is clear. I am now going to give some applications to what I will call a global Gauss-Bonnet. Okay. So for this I need a couple of definitions. So a solid triangle T in M is a closed subset whose boundary right, so is a closed subset such that T is completely contained in a coordinate in a coordinate neighborhood, and such that the boundary is a polygon with 3 vertices and 3 edges. Okay, so something like this. Okay. Then a triangulation of my manifold is a collection which I will denote by script T. So there are it is a finite collection of these triangles such that each Ti is a solid triangle the union of these Ti's covers all of M, and if I is not equal to J, then Ti and Tj either intersect along a complete edge or just at a vertex, or they do not intersect at all. Okay. So for instance, you can have things like this, or you can have things like this, okay, but not things like this. Okay. So this is not allowed, or of course they may not intersect at all, that is fine too. So let V, E and F be the number of vertices, edges and faces respectively. So, the number of faces is just the number of triangles. Okay. So, then one defines the Euler characteristic So, one denotes it by chi m of this triangulation. This is simply the alternating sum of the vertices, edges and faces. Okay, so then the global sort of Gauss-Bonnet says the following. So, if M is compact without boundary, and of course all the earlier assumptions that it is still oriented surface etc., then we have this beautiful formula that the total integral of the Gauss curvature is simply 2 pi times this Euler characteristic. Okay. So, a couple of remarks are in order. One thing is that in particular the RHS is actually the LHS is independent of the triangulation, and hence the RHS also must be independent. So, this number is called the Euler characteristic of the manifold. So, this guy will then be independent of the triangulation that you have used. Okay. And similarly, the second point is that the RHS is independent of the metric. And is a topological quantity, because if you continuously deform your surface, clearly the Euler characteristic, I mean the triangulation will deform, but the Euler characteristic is going to be independent of the deformation, right. So, clearly the RHS is independent and is a topological quantity, and hence so must so must be the LHS. So, even though the LHS depends, I mean the Gauss curvature obviously depends on the Riemannian metric, the total Gauss curvature turns out is a topological quantity that just depends on the topology of M, right. So, this is quite a remarkable theorem. Let me just give you as a consequence, before I give you a quick proof of this, let me remind you of the classification of surfaces. This is a very classical theorem in differential topology, that every compact without boundary oriented surface is diffeomorphic to sigma g, where sigma g is basically just the usual sphere with g handles. So, you can imagine a cup with g handles instead of just one. So, in general this sigma g looks like this. and so on. So there are g of them, okay. So this is an example where g is 2, and in fact then this Euler characteristic is simply given by 2 minus 2g, okay. So then a consequence of this classification of surfaces and the Gauss-Bonnet is that we get this beautiful relationship between the total Gauss curvature to the genus. So this number is called the genus. Okay, so this is going to be 4 pi 1 minus g. So especially let me give you some special cases when g is 0, for instance. So that is m is diffeomorphic to the sphere. So in this case the total Gauss curvature is going to be 4 pi, and we saw that at least with the round metric on the sphere the curvature is 1 by the Gauss curvature is 1 by r squared, the area of the sphere is 4 pi r squared. So when you multiply them together you get 4 pi, but this theorem is much more I mean says something much deeper, that even if you sort of deform your sphere, so your sphere you can think of it as the sort of sheet of a balloon. Even if you deform your sphere without of course introducing cuts etc., the curvature distributes itself so beautifully that the total curvature still remains 2 pi, okay. Similarly if g is 1 then m is diffeomorphic to the torus, and in this case if you take the total Gauss curvature that is going to be 0 because the genus is 1, okay. So again if you look at the usual donut example, that has areas of positive and negative curvature. So the curvature is positive here, in the inside regions the curvature is negative, but again the curvature somehow distributes itself so uniformly that so beautifully that the total Gauss curvature is 0, right. So this is a remarkable theorem. So so as I said we are going to have to work a bit harder, so this lecture is a bit longer than usual. So let me quickly give you the proof of the global Gauss-Bonnet and then we can end. So so I want to say that the local Gauss-Bonnet implies the global Gauss-Bonnet by a simple combinatorial argument, okay. So let's quickly write down the proof. So let epsilon ij for j equal to 1 2 3 be the external angles of the triangle Ti, okay, and let alpha ij, which is going to be pi minus epsilon ij, be the interior angles. So the reason for considering the interior angles is that if you consider various triangles, then the interior angles basically at any vertex will sum up to 2 pi, okay. So then by the local Gauss-Bonnet we have the following. So if you apply to each triangle, so for the triangle Ti we have the sum of the external angles, which is just pi minus the interior angles plus the integral of the normal curvature on the boundary plus the integral of the Gauss curvature on the entire region, this is equal to 2 pi. So now I sum over all the triangles. So there are capital F number of triangles. So if you sum over I from 1 to F, if you sum up the total Gauss curvature on each of the triangles, you are basically just going to get the total Gauss curvature on all of your M, right, because these triangles do not overlap in any set of positive measure. So the only places where they intersect are possibly vertices and edges, those are not going to add to your integral. So you can replace the final term by simply this, and then that is 2 pi times f. Okay, so let me now look at the this term. So so the point is that you might have triangles that share a common edge, but now notice what happens when you try to positively orient the edges of the curve, edges of the triangle. So for the triangle at the top, the bottom edge will be will have an orientation, let us say, going from left to right, but if you try to orient the triangle at the bottom, then what is now the top edge for the triangle at the bottom will have the exactly opposite orientation, right. So now when you sum up the contributions of the normal curvature, they will basically be equal and opposite on these two edges, so they will cancel out. So this entire sum disappears. Okay. So this sort of trick, if you recall, is also used a lot when you prove Green's theorem, for instance, right. So how do you prove Green's or Stokes' theorem? You break up your region into a mesh, and then you say that each of these boundary integrals can be dealt with by the fundamental theorem of calculus, and then on the boundaries that are inside the region, they all sort of cancel out exactly, right. So this sort of trick is also used in the proof of Stokes' theorem. Alright, so that takes care of this term. For the first term, you basically have 3 pi times f minus, so let me go back to the first term. So when you sum up pi over, there are 3 sort of vertices, so you get 3 pi, but then you have to sum over all possible faces, so that gives you 3 pi f. So this thing is going to be 3 pi f, and similarly if you sum up all the possible interior angles at each vertex, I have already commented that the interior angles sum up to 2 pi. So the total will be basically 2 pi times the number of vertices there are. Okay. So the first term is basically 3 pi f minus 2 pi v. The second term goes away, as I have explained, and then you have this Gauss curvature term that ought to be equal to 2 pi f. So if you rearrange, you basically get that the total Gauss curvature is precisely 2 pi times v minus f by 2. Okay. So now the final sort of argument, how do we insert the number of edges into this equation? We note the following, that each edge is an exactly, by the way, I should have mentioned that that these things cancel out precisely because there is no boundary to M. Okay. So all of these sort of edges must be accounted for when you do this cancellation, okay, because there is no boundary of M. So similarly here each edge is in exactly 2 triangles, right. On the other hand, each triangle has exactly 3 edges. So then if you do the bookkeeping, that basically means that 3 times f is equal to 2 times the edges, right. Okay, so that just means that the number of edges is 3/2 the number of faces. So if you now come back to your formula that we derived earlier, then I can rewrite this as v minus 3 by 2 f plus f, right, because minus 3 by 2 f plus f is just minus f by 2, which is exactly what I claim. This is the Euler characteristic. Okay. So that completes the proof of our global Gauss-Bonnet. So it all now boils down to proving this local some angle property or the local Gauss-Bonnet. Alright, so that is it for this lecture. In the next lecture I will set up the main technical tool in proving the local Gauss-Bonnet. So that is the so called rotation angle theorem due to Hopf, and then in the 30th lecture we will sort of put all the pieces together and complete the proof of the Gauss-Bonnet of the local Gauss-Bonnet theorem. Alright, so that is it for this lecture. Sorry that it was a longer lecture than usual. I think the next lecture might also be slightly longer, but then the 30th lecture would be short because we would already have had all the technical pieces to put everything together. Okay, so thank you for your attention, and I'll see you in the next lecture.